Hello and welcome to Gaffy's Grinds. In this video, we are going to do a little bit of a walkthrough on some typical questions that we might get about the titration experiments in Leaving Cert Chemistry. We're going to focus on this titration, which is usually the first one you will do. Okay, so the title is Titration 1 to standardize a solution of HCl using a standard solution of sodium carbonate. All right, so at this stage, you probably should have made a standard solution of sodium carbonate. Standard solution means we know the exact concentration. We know this because we have accurately measured out the quantity of sodium carbonate and made it up to an accurate volume. So we know exactly how many grams of solute are in there, and we know exactly the volume of the solution. So we can work out the exact concentration. It's very accurately known. We're then going to use that to find the concentration. That's what we're saying, standardized, to find the concentration of an unknown solution of HCl. I'm not going to talk too much about the theory of titrations. I've done that in other videos. In this video, we're just going to focus on some of the questions you might get asked, show you how to do the calculation. All right, some things to know. All right, so let's have a look here. Our HCl solution, because it's the acid, always goes in the burette, and our base always goes in the conical flask. So the Na2CO3 goes down here in the conical flask. Our indicator in this case is methyl orange. And the reason why we use methyl orange is because this is a strong acid, weak base titration. So there is like a little acronym to help you remember this, and it's SORB-MO. Okay, so strong acid, weak base, methyl orange is the indicator. If you've got a strong acid and a weak base, methyl orange. Color change we expect to see here is it'll originally be yellow because it's the methyl orange is mixed with a base and it's yellow in a base. And as we add acid and we get to the end point of our titration, one drop turns it acidic and that causes the color change to red. So the color change is yellow to red. Here is your balanced chemical equation. Right, so at this stage, again, if you haven't already answered these questions, so my class are watching this as a way of correcting their answers, then you can pause the video at this stage and have a go at these three questions here, 138 to 140. So pause the video and do that now. All right, so you should only be playing if you've already answered these, and here are the answers. So the question says, which solution in the experiment is the standard solution? The standard solution is the one we know the exact concentration of, and that's the Na2CO3. Okay, or sodium carbonate. So that solution is the standard solution. How exactly do you know? Well, we made it up accurately. We know its exact concentration. So we know its concentration. That's how we know it's the standard solution. Well done if you said those two answers. The last thing is describe two procedures that should be done with the conical flask during the titration. Okay, two procedures that should be done. All right, the first one we want to talk about here is, well, as we add, we don't just leave the flask sitting there, okay? So if you didn't think about that, maybe pause the video and add. What do we do with the flask as we're adding? Pause the video, talk about that now. Okay, so as we're adding the acid, we should be swirling, continuous swirling the conical flask. So continuously swirl the conical flask, or mix, you could say. Swirl the conical flask. Swirling is kind of describes the type of movement we do. Okay, that's one procedure. And a second one, what else should we do? Okay, so again, if you didn't get a chance to do this, something else we do to the flask during the titration. Pause the video and write down an answer. Okay, so what we should do is we should wash down the sides. During the titration, we stop every maybe 5-10 centimeters cube and stop and wash down the side of the flask. So wash down the sides with deionized water. Hopefully those questions weren't too challenging. They're pretty just procedural stuff that we should know, just kind of factual stuff. All right, let's get on to a typical type calculation then. So it says here the following is a typical calculation from an exam question. Your teacher will show you how to identify the important information in the question. Okay, so I am going to show you how to do this. My students should know how to do this already. All right, so what you usually get is you get a piece of text with some numbers and some important information in there. Then you always get a balanced equation given to you. Here it is, okay? Now, my suggestion is before you read any of the text, I always ask my students to write out the balanced equation on your page. Of course, this is going to be on your exam paper, and you're going to have a blank page in front of you. So always a good idea to rewrite that out. So I'm going to go ahead and write that out. Actually, I'm going to get you guys to pause it and just copy it exactly the way it is. Pause the video and do that now. Okay, so what you should have done is, this is what you should have. 2HCl plus NaOH react to give NaCl plus H2O plus CO2. Now the products we're not that interested in, okay? You can almost forget about the products here. All of that stuff is not really important. What we're interested in is the two reactants and how do they react and what proportions do they react. The first thing I want you to do, this is an acid-base titration. I want you to pause the video and write above which one is the acid and which one is the base. So pause the video and do that now. Okay, you should know from doing acids and bases that HCl is hydrochloric acid, so this here is an acid. And sodium, oh, actually, I have this wrong. This is not the correct base. Sorry, this is Na2CO3. Apologies, that's my bad. This here is the base. Okay, so that's the first thing to identify, the acid and the base. Next thing I ask my students to do is I ask my students to take two arrows like this, coming from each of these reactants. Like that. And on both of these arrows, we need for each of these things, we want a concentration and we want a volume used. Okay, so we got to go to the text for this. This little blurb will give us this information. And this is what students typically find the hardest to deal with. This is where you have to really get used to reading these things, okay? And think about the order that you're seeing the words in and which thing goes with which. And I'm going to try and color code this using a highlighter. Remember, we're looking for information about the acid and information about the base. So I'm going to highlight everything about the base in blue, and I'm going to highlight everything about the acid in red because they're the colors I used over here. All right. So first of all, it said the student determined the concentration of hydrochloric acid. Okay, so there's red. And it said determines the concentration. So that probably means that that's what they're finding. This is what they don't know. So there's a good idea that this is unknown molarity, unknown moles per liter. By titration with 25 cm cube portions of a 0.05 molar standard solution of anhydrous sodium carbonate. A lot of information in that sentence, but essentially what it's saying is that we use 25 cm cube portions. The concentration was 0.05 of the standard solution of anhydrous sodium carbonate. So if you don't identify those properly, which numbers go with which thing, this is going to be very difficult. You're never going to be able to get the calculations right. So this is referring to the base, 25 centimeters cube portions of a 0.05 solution of sodium carbonate. So all these things go together. All right, so now that I know that, we're going to go and fill that information in on the base. Okay, so I know the concentration was 0.05 molar. So I'm going to write that down here. Base was 0.05 m. And the volume were 25 centimeter cube portions. Now, I know that titration calculations are always better if you have the volume measurements in liters. So I'm going to do a little bit of rough work here at the top to turn 25 cm cubed into liters. Now, again, I've shown you how to do this before using a conversion factor method. We times it by a fraction, a conversion factor that goes between cm cubed and liters. Okay, we want to get our answer to be a certain amount of liters, which means I need to cancel centimeters cubed in units because that's what I'm starting with. So if I put centimeters cubed in the denominator of this fraction, they will cancel with those. And if I put liters in the top, then I'm left with liters, which makes sense because that's what my answer should be in. So the next thing is, what's the relationship between centimeters cubed and liters? So there's 1 liter for every 1,000 centimeters cubed. And that's a fact you just need to know, 1,000 centimeters cubed in a liter. So now I've got a calculation to do, 25 times 1 over 1,000. So 25 times a fraction 1 over 1,000. And that gives me 0.025 liters. 0.025 liters. So now I can write that down here as my volume, 0.025 liters. Now, some of you may even be able to do that calculation in your head. If you've got 25 cm cubed, then what do we got to do? We got to move the decimal place 1, 2, 3 places to the left to turn it into liters. And then we can say that that's in liters. You guys, if you get really good at this, you can do that really quickly, okay? So some of you, if you're able to do that maths, then that's brilliant. That's going to save you some time. But always convert to liters first. All right, let's find out more about the acid because we don't know much about that yet. All right, reading carefully. So I'm switching back to my red highlighter here. It says the portions of sodium carbonate solution were measured into the conical flask using 25 centimeter cube pipette. Okay, that's not really that important for this. That's just saying how it was measured. We know we were using 25 centimeter cube portions here. It's just telling us we did it with a pipette. The hydrochloric acid solution was added from the burette. The mean titer was 20.8 cm cubed. So this is the titration value of the acid that we added. And this word here says mean, which just means average. And you should know that in a titration, you always take the average value of your accurate titration values. So essentially, this here is the number that we need to use as our volume. It's just telling us that this was the average volume. This is what we should use in our calculation. And again, this is for the acid, but we want this as liters first, just like we have here. Okay, so we're going to put a certain amount of liters here. So in red now, I'm going to do that calculation. We got 0. Oh, sorry, no, we don't. It was 20.8 cm cubed. And again, I'll show you the long way of doing it. Times by cm cubed per liter, like that. And there's 1 liter for 1,000 cm cubed. Cancel your cm cubes, leaves liters as your units, which is what we want. And you should get 0.0208 liters. Okay, so that's what we can fill in here. I'm going to just make this pen a little bit narrow. It's a bit 0.0208 liters. And remember then, if we go down to the question, it says calculate correct to 2 decimal places. That's actually, oh, that's a sneaky little one here. Okay, so your answer given to 2 decimal places, highlighting that to come back to later. The concentration of the hydrochloric acid solution in moles per liter, part 1. So straight away, we can say we don't know the moles per liter. So this here is question mark molar. All right, so now we're ready, almost ready to start our titration. Okay, we have the information. We have 3 knowns and 1 unknown, and we're going to have to work out the unknown. The next thing to do is think about, okay, the molar ratio that we're reacting these in. Okay, and you should know from this balanced equation that the 2HCl means that there are 2 moles of HCl for every 1 mole of Na2CO3. The next thing we want to do is find out how many moles then of Na2CO3 was used in each titration. You can easily work this out because we know how many moles per liter and we know how many liters we used, so we can work out how many moles we used and then find out how many moles of acid that would have reacted with and work out the concentration. That sounds like a lot of work, but it's really not too bad. You just got to practice lots of these, all right? So the first thing to do is start with the known. So this here, the base, because we know both values here, this and this is the known, and the acid in this case is the unknown. This is what we're trying to find, this guy, okay? All right, so let's go ahead and start with the known. Write down what we have. We have a 0.05 molar solution, which means 0.05 moles. Molar means moles per liter. Again, this is one of these facts you have to know. So we have 0.05 moles of Na2CO3 per or for every 1 liter. Okay, that's what molar means, moles in 1 liter. Now, we want to find out how many moles that is. So we want liters to cancel. So we've got to times by a certain number of liters up here in the numerator. And that is the amount of liters that we actually used, which was 0.025. So times by 0.025 liters, you'll notice that the 2 liters cancel out and we'll be left with moles of Na2CO3, which is good. That's what we were trying to find here. So equals, so let's go ahead and again, get you to pause the video and do that little calculation yourself. Okay, so hopefully you did that and you should have got 1.25 by 10 to the minus 3 moles of Na2CO3. Okay, so again, it's always a good idea if you're doing bits of it, bits of the calculation, and then hopefully when you go to do the next one, you'll be able to do a lot more of it or all of it. Okay, so the next thing, we know that we had this many moles of Na2CO3 in the reaction, in the titration reaction. The next thing that we've got to do is focus on, okay, well, how many moles? And we know that the ratio here is 1:2. So the base to the acid is 1:2. So what I'm going to do here is I'm going to times it by a conversion factor that has moles of Na2CO3 compared to moles of HCl. So I want these to cancel, moles of Na2CO3. So I put it on the bottom here, moles of Na2CO3, and then it will cancel there. And that means that moles of HCl is going to go on the top. Okay, and I'm going to go back to my equation again. Remember, HCl is 2:1. So it's 2 moles of HCl for every 1 mole of NaOH. So stick that in your calculator. You go ahead and do that calculation now. Pause the video and do that now. Right, what you should have got here, hopefully, is 2.5 by 10 to the minus 3 moles of HCl. So this is the moles of HCl used in a titration. Now that's not the final answer because we were asked for the moles per liter. So I'm going to go to the next line to do this, okay? So I'm just taking that same number and I'm going to the next line. So it was 2.5 by 10 to the minus 3 moles of HCl. And I want to know in what volume, how many liters was that for? And that was in this many liters because that's how much volume we use. So per 0.0208 liters. Now look what we're left with as our unit. Okay, moles per liter, which is what we were trying to find if we go back here. Concentration in moles per liter. All right, good. So we know when we do it this way, we know we have it right. All right, so go ahead and find the value then. Stick this in your calculator and see what the number is. Pause the video, do that now. Okay, and I am getting 0.12 moles per liter, which I can write like this, capital M, 0.12 molar. And remembering that it asked us to go to 2 decimal places. And this is the HCl. All right, so this is part 1 done, okay? All right, let's go back and check because there was another part. It asked us also to calculate it in grams per liter, okay? So let's go and do part 2 over here, make yourself a bit more space. All right, part 2, well, we're going to have to go from moles per liter to grams per liter. So what we just calculated is that we had 0.12 moles of HCl per 1 liter. That's what we worked out. And we want to go to grams per liter. So we want our answer over here to be in grams of HCl per 1 liter. Now you'll notice that the 1 liter and the 1 liter is fine. We want to leave that there, so we don't need to get rid of liters, but we do need to lose the moles, and we need to turn them into grams. Okay, grams up here. So we're going to times by a conversion factor that has moles of HCl on the bottom, so we can cancel moles of HCl and cancel with moles of HCl, like that. And then we want grams of HCl on the top, because that has to be in our answer over here. So grams of HCl on the top. And then look what we're left with. We're left with grams of HCl over 1 liter, which is grams of HCl over 1 liter. Okay, so that's how those unit analysis works. I've done lots of videos on them now. All right, so the question is, for every 1 mole of HCl, how many grams is that? Now that's, you work out the molar mass. You should know what I'm talking about. Pause the video, work out the molar mass of HCl. Right, the molar mass of HCl, there's 1 gram for the hydrogen atom and there's 35.5 grams for the chlorine atom, which means that I have a molar mass of 36.5 grams in 36.5 grams in 1 mole. So what I'm going to do now is I'm going to go ahead and I'm going to do this calculation, and you should pause the video and do the same. Okay, and you should only be watching if you have completed this now. And the answer you should get is 4.38 grams of HCl in 1 liter. This is your answer to part 2. And that's really as hard as this calculation gets for this particular titration. Okay, so well done if you've got all of those right. There's a couple more little questions here, okay, that are kind of recall questions. And I'm going to get you now at this stage to pause the video and have a go at these questions now. So 141 to 144. Pause the video, have a go at them now, please. All right, so from memory, again, I always ask my students to work from memory, not to copy stuff. We never learn anything when we copy. So trying to remember, if you make a mistake, that's when you fix it and that's when you learn from it. But if you're just copying, you're not actually having to think about it, you're not learning very much. So from memory, name the indicator. So you should have written methyl orange. Methyl orange was the indicator. Methyl orange is yellow in a base, and it was with the sodium carbonate in the conical flask in the beginning, so it was yellow. And when it got to the end point, the solution was just 1 drop turned it acidic, and that means that it went red. So yellow to red is the color change. Now these here are very important, easy marks on the exam. You need to know your indicators and you need to know your color change. And when you're asked for a color change, you need the before color and you need the after color like this. Yellow to red, yellow arrow red, or you could write a sentence yellow to red. That would be fine too. Okay, methyl orange, yellow to red. Gotta learn it, guys. All right, next one. The concentration of hydrochloric acid solution is now known. So we've just worked it out. Angela then says that hydrochloric acid is now a primary standard solution. Explain why Angela is wrong. Okay, this may be a tricky one. You may not have understood this one, but primary standard solution, this word primary means 1. So this is the number 1 standard solution. Now, number 1 standard solutions or primary standard solutions are ones that have been made up directly and they have been measured out exactly how much solute and exactly how much solution. We did not do that with this hydrochloric acid. We used the primary standard solution, sodium carbonate, which we did make up, to standardize another solution, the HCl. So we can't now call the HCl a standard solution because we didn't make it up. Okay, so the answer that I was looking for here was it wasn't made directly. So it wasn't made up directly, the HCl. It's only if you actually measure it specifically, the quantity of solute and the quantity of solution, that you actually can call it a primary standard solution. Now it's still standardized, we know its concentration, but it's not a primary standard solution. Instead, Angela should call it a secondary standard solution. Well done. If you got that by yourself, well done. If not, I hope you understand the differences between primary standard solutions and secondary standard solutions. Now, primary standard solutions are ones you make up. You use a volumetric flask, you add a certain amount of mass of a solute, you make it up to a certain amount of solution, and you know exactly to the gram, to the 0.1 of a gram, how much is in there. Secondary standard solutions are where we take that solution, a primary standard solution, and we use it in a titration to find the concentration of the secondary standard solution. All right, that's it, guys. It's probably the easiest of the titrations, to be honest. If this one comes up, you're laughing. It's pretty much exact same every year, except they change the numbers, right? They change the numbers, but it's the same process. You can find 7 or 8 of these in the past exam papers to practice and bang them out. And I'll suggest that you do that. Don't wait for me to do them out here. Go practice some now, okay? And if you have a problem, stick in the comments below the video here. Pick a year. Which one would you like me to help you with? Okay. All right, guys, that's it. I'll see you in the next video where we'll talk about the second titration.